Hi everyone, in today's lesson we're going to talk more about optimization problems. So we'll call this optimization day 2. So let's do an example. It says a metal box without a top is to be constructed from a square sheet of metal that is 20 inches on a side by cutting square pieces of the same size from the corners of the sheet and then folding up the sides. Find the dimensions of the box with the largest volume that can be constructed in this manner. So the biggest hurdle I think in these types of problems is really recognizing the picture. So I've put a little picture down here. You don't really have to copy this if you don't want to, but basically this is the piece of paper that is given. So in the problem, they tell you that the metal top box is going to be constructed from a square sheet of metal that is 20 centimeters on one side. So square generally means that the sides are the same. So I know this looks like a rectangle, but it was the best picture I could find. So this square would be 20 by 20, okay? And it says, in order to find this box, we need to cut square pieces of the same size from the corners. So that's what this little dotted edges mean, is that I'm going to cut these corners away. So notice they're all gone in this picture. So I need you to imagine taking this piece and folding it up, taking this piece, folding it up, and these. And if you fold it up, you should then receive, this open top box. So the idea is understanding the picture. So you're not going to be able to draw this every single time, but what you can draw is I'm cutting out a corner, and then I have a solid piece. Cutting out a corner, solid piece. Corner, corner, piece, corner, corner, and then piece. So that's really what you're doing. You're cutting these 4 pieces away. That's why we put them as dotted, so that we can fold them up like we did here to create that open top box. So when you're labeling your picture is this entire thing is 20. But once I take away this distance here and this distance here, we no longer have 20, right? We have a different scenario here. So if we don't know what the boxes are that we're cutting, we could call it X. So if this is X and this is X, basically we're starting with 20 and taking away 2 X's. So this highlighted piece right here is just 20 minus these 2 X's. So that's what you're going to label here, 20 minus 2X. Now, same thing would go on the vertical side, right? If this distance from here to here was 20, and we took away the 2 pieces that we don't know, right? So this whole thing from here to here is 20. I'm taking away this and this, which we could call X as well. So it's going to be the same thing. This would be 20 minus 2X. So those would be the dimensions of the base. Now, in these questions, we're actually not going to have a helper equation because they're not giving us anything else that we need to know about this. So all we know is that we're going to go straight to my maximize and minimize equation. So we have to read the question. What is it asking? It wants you to find the dimensions of the box with the largest volume that can be constructed. So they're trying to find the largest volume. So since that's the piece we want to find, that's what's going to be the maximize or minimize equation. Now we need to know the volume formula for a rectangular prism. That formula is length times width times height. Now it just so happens that we have a square, so my length and my width are going to be the same. So it doesn't matter which one you label which. I'm going to label this as my width, and we're going to label this as my length. So we can go ahead and put that into our equation. So the volume is length, 20 minus 2x, width, 20 minus 2x. Now the height is the part that's very difficult to visualize. So if you look at this picture that I have here, once we put these sides up, this side up, this side up, and all this, we now have a height of the box here. So this would be my height. And the way that you get the height is really from these X's that you cut out, right? So my height is just going to be X. Now, if this is difficult for you to visualize on this video, that's okay. We're going to go through this tomorrow and maybe I'll show you exactly how it's done so that way you can really visualize it. But the key concepts is that you, in order to get the new width and the new length, you have to subtract two x's. And the height is always going to be that x value, right, that you have there. So now let's answer the question. So we want to figure out the largest volume, and we know largest volume is another way of saying maximum, right? What is the maximum volume? So we need to find the first derivative. So first, let's rewrite our v. I'm just going to put it here so I have more space. So my volume is 20 minus 2x times another 20 minus 2x times x. So we can't take the derivative as it's written in multiplication form, so we're going to have to do some simplifying. So I would suggest double distributing these first two pieces and then multiplying it by x. So I'm going to ask you to pause the video and double distribute this and combine like terms, and then hit resume when you're ready for the answer. All right, so this is what I got. And I need to multiply this by x. Now, before I multiply it by x, I'm going to clean it up a little bit. So I'm going to put the highest exponent first, so 4x squared. I'm going to combine these like terms and make it negative 80x, and then plus my 400. Now it's much neater and cleaner that I can now multiply by x. So I'm going to distribute the x to all three pieces. So 4x to the third minus 80x squared plus 400x. So now that it's cleaned up, we can take our derivative. So I'm going to use a different color for derivative. I will call it v prime. So let's use the power rule. 4 times 3 is 12. Decrease the power by 1. 8e times 2 is 160. Decrease the power by 1. And the derivative of 400x is just 400. So just as we did yesterday, in order to find where it's maximizing or minimizing, we need to do the first derivative. So we're going to set the derivative equal to 0, and we're going to solve. Now this equation seems a little bit scary to solve. So my suggestion is, since they're both or all of them are even numbers, I would try dividing by 4, maybe dividing by 6, seeing if that works to take out a GCF first. So I think you can divide by 4. And if you do that, you're going to get 3x squared minus 40x plus 100. And because my leading coefficient is bigger than 1, we're going to have to do guess and test. So 3x and x will give us 3x squared. And we need the factors that multiply to 100. So I'm going to test a value first and see if it works. I'm going to try 10 and 10 just because they're closest together. I know 10 times 10 gives me 100. So I'm going to test my outers and my inners. So this is 10x and this is 30x. And that's absolutely going to add to this negative 40 if I make them both negative. So negative, negative will make this work nicely. So we need to now find my t-chart, right, to finish the solutions. So we've got, I'm just going to maybe do the t-chart down here. So we've got 4 equals 0, I need to reject. And I have 3x minus 10 equals 0. And I have x minus 10 equals 0. So the right side's easy. I can just add 10, and I get x equals 10. And the right side, the middle side, excuse me, needs a little work. So I can add 10 to both sides, divide by 3. So we get x is equal to 10 thirds. So we've got two possibilities here for x. Remember what x is. X is this part that we're cutting out. So we can't have two answers, so we have to determine which one will give us the maximum area. So in order to do that, we need our f prime number line. So I'm going to just put this here to the left. So here is my f prime. Or in this term, maybe we should actually label it what we're using. We used over here v prime for my first derivative. So we can label this as v prime instead. And we're going to put on here 10 thirds and 10. So 10 thirds is a little bit smaller than 10. And then we can put the 10 here. If you put 10 thirds into the calculator, you should get 3.3 repeated. Sometimes the decimal equivalent helps a little bit. So what you're going to do now is you're going to go to your V prime number line, which is here, right? Your V prime equation. And you're going to use this and you're going to substitute some values. And you're going to see where it's positive and where it's negative. You can put this, if you'd like, into the y equals, test a value that's less than 3.3, one that's in the middle, and then one that's bigger, and then hit resume when you're ready for the answer. All right, this is what I got. So what this tells us is that I'm increasing from here to here, I'm decreasing from here to here, and I'm increasing from there to there. So this is clearly the minimum value, and this one is my maximum value. So we know that when x is equal to 10/3, we will have our maximum volume. So let's just make sure we answered the question. So they want to know, what are the dimensions of the box with the largest volume? Okay, so dimensions is something a little bit different. Dimensions are length by width by height. And we know from our equation before, height was our x. So if we have x, x is equal to 10/3. So that is our height. And we can use centimeters. Now our length and our width are the same. They're 20 minus 2x. So if you figure one of them out, then you can just copy it for the other. So let's do the length. So since x is 10/3, I'm just going to substitute 10/3 for x. So 20 minus 2 times 10/3. So if you put that into the calculator, you'll get a decimal, but let's keep it as a reduced fraction. So take a second, pause the video, plug it in, and hit resume when you're ready for the answer. All right, so I got 40/3. So that would be my length, and it would also be my width, because 40/3, same thing for length and width. So to really answer the questions, when they ask for dimensions, they want length by width by height. So length by width by height are our dimensions. So 40/3 centimeters by 40/3 centimeters by 10/3 centimeters. So really, this is your final answer. All right, I know there's a second example, but we've talked a lot. So if you'd like, you don't have to solve it, but try to see if you can at least set up the picture. And we can go over the rest of this tomorrow. All right, have a good night.